With the trapezoid, excuse me, trapezoid's defined by just having one set of parallel sides. So it's still a quadrilateral. So it has one set of opposite sides parallel. Okay. Other than that, a regular boring trapezoid doesn't have much aside from that. One of the things you will see with the trapezoids pretty regularly is if you've got parallels above and below, the sides that connect them, those two angles are always supplementary, as well as these two angles over here. These are also supplementary. Reason being is that if you drew out the lines longer, you'd have your two parallel lines cut by transversals, and then you'd have consecutive interior. So technically on both sides, the two angles that connect the parallel sides, those two will always be supplementary, all right? The ones that are on the same line, there's really no correlation to them with the regular trapezoid. When it gets to the isosceles, then something else will happen. Okay. So you've got this one set of opposite sides that are parallel. The trapezoid that most of you guys are used to seeing is what you would call, actually, I'm just doing this on the other side, is the isosceles trapezoid. Oops. So the regular trapezoid, again, just has that one side, one set of sides that are parallel. The isosceles still has the side that's parallel, but it's got those two legs that are the same. Okay. That's the one that you guys are more accustomed to seeing when you deal with the trapezoid. When you guys draw one, that's usually what comes to mind. So with it being isosceles, what's up?
Is like the one side regular, is one side like straight and the other side's angled?
It doesn't have to be. It could be either way.
Okay.
Yeah, they're just not equal length. Okay. Once they become equal length in between the two, you wind up with the same idea as you would with an isosceles triangle. You wind up with two sets of base angles that are congruent. And then, again, these are still supplementary on both sides. And then really the only other thing that comes up with the isosceles one, and it's not even one that you can really show very easily, is is that the diagonals are congruent. They have congruent diagonals, whereas the other one doesn't. Okay. Again, it's tough to draw that in. It doesn't bisect anything, like a regular quadrilateral parallelogram did. These guys just have those couple little bits. And like I said, you guys have all seen this before. And what from there? Okay. Let's see, what else is there? Oh, I know. Both of these guys have what's called a mid-segment. And you guys saw this with triangles. They just happen to show up in trapezoids as well. When you have a mid-segment, remember it means it's a segment that connects the midpoints. Okay. Mid-segment is the segment that connects midpoints, and it's equal to, just like we did this before, this mid-segment is equal to half the sum of the two sides it doesn't touch. No, but not touched. Okay. Usually in trapezoids, they call those the bases. You guys remember that? When you did area stuff, you have two bases, base 1, base 2. So if you want to think of them in terms of bases, or if you want to think of them in terms of just the sides they don't touch. It's really easy. We did this same exact style of a problem with triangles. where the mid-segment was equal to half the side it didn't touch. Well, now it's just equal to half the sum of the two sides it doesn't touch. So just like, what was it? 2 weeks ago when we did this, we wrote it two different ways. We said the mid-segment was equal to half the sum of the two sides. Or we would say that we would double the mid-segment to equal the sum of the two sides. Okay. It can go either way. Yes, ma'am. Yeah. I don't know if there's some off. It should be. Yeah, there's some by my computer. Okay. Again, this isn't anything difficult. I know you guys have all done this. I know that the only thing that's going to be different here, instead of just half the side that we did with the triangles, now you have to add two things together. Ooh. I know, it's a lot. Okay. Aside from that, the trapezoid stuff's pretty easy to work with, and I should be all right. For example, let's see. Oops. An example like this would be one where you have your, just put that in. That's an example of what a mid-segment looks like, because it connects midpoints. The reason we know that those are midpoints is because if you look at the tick marks, they're cut in equal portions. So what would happen here is you make a decision. Do you want to take half of something or you just want to double something? I say you usually go with the doubling of it. It's a little bit easier to work with. So you would just have to double the mid-segment and set it equal to the sum of the two sides. Double the mid-segment equals the sum of the two sides. Alright? And boy, does this look just like every other algebra problem we've done for a long time. 2x and 4 is 4x minus 2. Subtract the 2x, add the 2 coming back, and you get x is 3. Real easy way to check this. What's 4 times 3? Subtract 10, you get 2. What's 3 plus 2? 5. So that's 5 here. So what's 2 plus 8?
7.
And what's half of 10?
5.
And it's that quick and easy. Okay. Mathing these things are pretty easy. Here. Again, these are mid-segments, or this is the mid-segment. Take a second to figure out what x is. Please and thank you. So hopefully if you did this quickly, and this is not too bad. Say double your mid-segment equals the sum of 6x minus 12. And that just matters quick solves. 4x and 20. Subtract 4x, subtract the 6. And hopefully you got 7. Yay. Might be working the crowd. Yay. Could we make this more difficult?
Yeah.
Yeah, we could, wasn't it? Really, the only other weird thing that can happen. Well, that's before. Oops. I'm not gonna do that one. So next thing then we have what is called the kite. Yeah, that flew. Like that? Sure. Anyway, easiest way to think about a kite, obviously it doesn't have a tail. Easiest thing to think of when we not define one is think of it as two isosceles triangles put together and they share the same base. Okay. Think of the kite as two isosceles triangles sharing the same base. Now the kite's going to have a bunch of extra weird, I don't want to say weird, but it has a couple more properties than the trapezoid does. You have, so the other side here. Here we'll have two sets of non-opposite sides congruent. What that means is that they're, like in all the other parallelograms, there were opposite sides that were congruent. These guys, they're non-opposite, so they're just next to. The diagonals are perpendicular to each other. The angles that are between the two different sized sides, I don't know how to write this out cleanly. Angles between the two different sides are congruent. Here's what I mean by that. See how these are the two different sides? One tick mark, two tick mark? The big angle that's between them are the ones that are congruent. Okay? Those two big angles are going to be the same. The reason that that works is because if you've got isosceles triangles, you know that those two space angles have to be the same because isosceles, and then those two on the bottom have to be the same. So if you're adding the same things together, you're getting a congruent triangle or congruent angle. So that's why that works. Also, the diagonal between the congruent angles is bisected. So this part here. What else is there? That's where that all shows up. It just looks kind of weird. With right angles, that means you're going to get Pythagorean theorem again. Notice that you've got the right angles in the center there. I wouldn't call it center, but in the inside of the kite. And then those outer pieces, the sides of the kite, if you will, are the parts that would be the hypotenuse. Those would be the C values. So we got a couple examples of that. I know that all of you guys have worked with this. It's just you probably haven't seen some of the terminology with the perpendicular and all that. Okay. So far, so good? Oh. Okay. Let's see. For example, this is going to be really difficult. Let's find. Oh, do you guys know what the easiest way to draw a kite is? Because I'm terrible at drawing these. I finally learned how to do this last year from someone. If you just draw, if I was going to draw this one. Draw like the plus sign or a T and then just connect the sides. It's not pretty, but it works, I guess. I don't know. I am not an artiste at all. How many sides does a kite have?
4.
So how many degrees does it have on the interior?
250.
That doesn't change. These are all what we call quadrilaterals. They all have 4 sides. They all have 360 degrees. That angle M, is the angle M between the two different sides that are congruent?
No.
Yes, because the tick marks. What does angle K have to be? Has to be the same. And then again, as we were saying, there's a total of 360 degrees. Just add all these up. So you have 360 back out the 120, gives you 240. 88 and 88, I believe, is 176. Just subtract out. And again, you'll notice that the math here shouldn't be so 8. It's 6, 64 up front here. And we go from there. Okay. Should not be very difficult. Okay. Same thing goes for sometimes you have to find that missing angle in the middle. Oops. Now in this case, angles M and K, they still have to be congruent to each other. But what would you do? They have to be the same. How many degrees are in a quadrilateral? 360. What's 60 and 50? Back out the 110, and you're left with 250. What does each angle have to be?
175.
You cut it in half, and you get the 175. 125. Get the 125s. Because those two have to be the same. Right? Because they're between the two different sides that are congruent. As we go through. Let's see what else is there. That's pretty much all of those. Does anything change here? Is it okay to get a decimal for an answer? Why? I mean, if you get X, if you have a decimal in answer, can it still work? What's half of 111? It's not going to be an even number, is it? Is it okay to get a decimal? It's okay. It happens. All right. You guys got to remember that a lot of times, not every number is going to be clean. It's not so much, especially as we get into the second semester. It's going to happen tons and tons and tons more. So again, these two, since they're between the two different sets, they have to be equal. So you just divide out. You get 55 at 5. And mathing of this is really simple. Just making sure you understand what you're looking at as you're going through. Mid segments, take a second, try this one again. Solve for X, please. So there's a couple ways you can do this. Since the two sides, the parallel sides, are numerical, you could just find the average of that right away and set it equal to the 2x minus 1. Or you can just do the whole formula, double the middle, set it equal to the sum of the outsides. Either way would work. And with any luck, you got 14 for x. So hopefully it wasn't too scary. Let's see, I don't know about the decimal. I'll show you the kite one that shows up. But I was saying with the kites, sometimes you have to find the side lengths. So like they were saying earlier, or we had said earlier, we know that when you have a kite, the diagonals are perpendicular. Okay. The diagonals are perpendicular, and if it wants you to figure out what the outer, whatever the side lengths are on the outside, notice you just wind up with Pythagorean theorem. Okay. Your side lengths here, since this is across the right angle, these are always going to be your C values. And it's just a matter of typing it in the calculator correctly. Right. So if you do this right, we would get 8 squared plus 9 squared equals C squared for the hypotenuse. 64 and 81. So in your calculator, if you type all that in, so 8 squared plus 9 squared, hit enter, you're going to get 145. Now, the multi-view calculators will give you simplified radical form, is what we're looking for here. So you get second square root of your answer. And it's telling you it's the square root of 145. That just means it can't be simplified. Okay? And just leave it. All right? And that would be the perfectly legitimate answer. That side length is the square root of 145. You do the same thing for the other one, down here. Again, this time would be 9 squared and 7 squared. So back to the calculator. 9 squared, 7 squared, enter. Second square root of your answer, and leaves it again as square root of 130, and that's fine. Does not need to give you a decimal. Now, obviously, the other two sides would be the same. ST would also be the root 145, and TU would also be the 130, because, like I said, it was a kite. Right? Notice how they, see how the 9s are both above the one diagonal, and the 8 and 7 are to the left of the other diagonal? That means they correspond to the same segment. You'll see that a lot, that way you know the full lengths. Let's see, what was the other one? You guys try this one. So again, figure out what VS is and figure out what UT is. Take a second, figure those out.
Is 12 the long one down?
Yeah, it is. Again, notice how it's to the right of that one, and it's on the inside. That means this goes with the diagonal. Take a second, figure out those two side lengths, please, and thank you. You do this right. So you take the square root of 50, you should have gotten 5 root 2 for the VS segment. You did that right. And then for the other one, when you write that out, you had 5 squared, 12 squared. That was for UP squared. You would have got 169, which would have been, take the square root of that, you got 13 for the other part. If you did it right. Remember, type it into the calculator. Start using that answer button. It will make your life a lot easier as we get to second semester. We do a lot more calculations. The more you get used to using the answer button, the easier it'll be. A lot less rounding error you'll wind up with. Okay. It's one of those nice little tricks. I almost forgot, one of the other weird things that does show up on the kite, and I apologize for forgetting to mention this one, is, does everybody agree that there's 2 different diagonals? Generally, there's a long diagonal and a short diagonal. Because if they were the same length, it wouldn't be a kite. You okay with that? The longer of the 2 diagonals bisect the angles that it runs into. Okay? The longer of the 2 diagonals bisect the angles that they run into. So like these two would be the same, and these 2 would be the same. Okay? Because they're different angles. All right. For example, let me show you here. I think I had it. No, I didn't. Let me pull this one up real quick. It's a 6, right? Yeah. The textbook does a problem like that with these, where they ask you to find all the numbered angles, and it's a really easy thing to do once you figure out what they're looking for. So, in one like this, if you had to figure out, you're going to figure out all the different angles here. Excuse me. You start going through to figure out all the angles. We know what happens at the 2 diagonals. What angles are created at the diagonals? 90s. Okay. So you know around 1 and 3, those guys are all 90. Okay. How many degrees are in a triangle? 180. So if I back out the 90, and then I back out the 35, gives you what? 55, I believe? Okay. So it gives you 55 for here. Now, we also know that this diagonal is between the 2 angles that have to be the same, so it's bisected. 4 has to be 55 because this becomes a shared side, reflexive, if you will, and you get 2 sets of congruent triangles, so they're mirror images of one another, so this becomes the 55 here. Also, because it's isosceles, these have to be the same, and this one has to be the 35 as well. Okay. It's not that it's difficult, it's just that it takes a second to figure out what you're working with. Okay. And obviously, if we had to get into the other triangle, the other side there, you'd have to know one of the angles to make it work. There's nothing that tells you anything else specifically off of that. Right. Does that make sense? It's a little weird. I just want to make sure you guys saw that these angles are always bisected. This is the longer one, and these 2 will be the same, and these 2 will be the same. So, let's see. I think there was one more. This one. So let's do this. There's enough info here. This is like I was just saying. Take a second and try to figure out all the missing angles. There's 10 of them. Well, 1, 2, 3, and 4 are pretty easy. Those all have to be 90. Okay. Back out 34 to get to the angle 9. That gives you what, 56, I believe? Means this is 34, 56. 5 has to be 46. It's bisected there. And then 10 and 8 both have to be 44. Okay. Like I said, this should not be very difficult. Right? Homework already posted on the calendar. Let's see, I'll pull that up again real quick. It's in the textbook. You got the PDF file also. If you want to take a second, take a look at it here. I honestly just forgot what numbers they were. Copy this real fast. Wasn't exactly sure how far we're going to get, so oops. There it is. So it's on page 394. I want you guys to do numbers 8 through 36 by 4s. Every other even, if you will. And then those last 6 are, I think they're like true-false ones. The parallelogram has this, that kind of thing. So just let me go through. Make sure you get the PDF, screenshot the PDF or whatever on the Chromebook, so if you lose internet, you can still get it through. And go from there. And go from there. All right? Questions? Knock it out.